Hi everyone, my name is Neha and this is the 19th lecture on Introduction to Automation. In this lecture, we're going to continue the stepper motors. We're going to start with modes of operation in stepper motor. First mode is single step mode. In single step mode, the operation is based upon the fact that each step in the stepper motor is completely independent from every other step. That is, the motor can come to a stop or it can even reverse the direction at any time. Therefore, in this type of stepper motor, the controller has complete and instantaneous control of the motor's operation. And also, there are higher chances that the controller will not lose the count because each step in the stepper motor in this type of mode is very well defined. This type of mode has a disadvantage also, which is that the motion of the motor is slow and it is choppy. A typical single step rate in the single step mode is 5 steps per second, which translates to 12.5 RPM for a 15 degrees step motor. So here on this curve you can see this is the position which is in degrees, and on the x-axis we have time, and this represents the steps. So you can see this particular portion of the curve represents the one step. Now let's see the second mode, which is the slew mode. This mode is also called unidirectional mode, and this type of mode is pretty close to the operation of a regular electric motor. And in this type of mode, the rotor it will always experience a torque and it rotates in a smoother and continuous way. So in this slew mode, the stepper motor it basically cannot stop, or it cannot reverse direction instantaneously when compared with the previous mode. If in case the stepper motor is made to stop in this type of mode, or maybe if it is reversed, then the rotational inertia of the motor would most likely carry the rotor a few steps ahead before coming to the rest position. So in this type, the step count integrity will be lost. Now to solve this problem, there is one solution, and that would be to maintain the step count in the slew mode by slowly ramping up the velocity from the single step mode and then ramping down at the end of the slew. This means that the controller must know ahead of time that how far the motor must go. Then only this problem can be resolved. So in this mode, due to high frequency, the step size will look like this, and you can see this is pretty close to a linear curve. Now let's see next, which is the curve between torque and speed for single step and the slew mode. So on the y-axis, we have the speed, which is the steps per second. And then we have torque on the x-axis, and then we have two curves between torque and speed. This is the single step mode and the other one is the slew mode. And then on the x-axis we see different types of torques are shown over here. You can see a detent torque, a dynamic torque, and then a holding torque. So we're going to see what these are. The detent torque we have already discussed in the last lecture. It is also called residual torque, or we can say a magnetic torque in the motor. So this torque required to overcome the force of permanent magnet when the power is off, and you can actually feel this this torque when you manually rotate the unpowered motor. Then there is a magnetic torque you feel, that is called your detent torque. And then you have dynamic torque. So this dynamic torque is occurs when there is a maximum running torque, and it is obtained when the rotor is lagging behind the field poles by a half a step. So at this point, when the dynamic torque occurs, the rotor lags by 45 degrees. And then we have finally the holding torque. So this holding torque is the highest stall torque. It results when the motor is completely stopped but with the last pole still energized. So if the last pole is energized at that time, whatever the torque is, that is called your holding torque. And this type of torque is very similar to the detent type of torque, because it represents the amount of external torque which is needed to rotate the motor against its wish. Now let's see next. Next we have excitation modes of permanent magnet stepper motors, and the first excitation mode is the two-phase stepper motor. So you can see here, this represents the stator field coil. This is also the stator field coil, and this is the wiring diagram. You can see 4 coils have been represented: first, second, third, and fourth. And then at the center is our rotor. So right now the rotor is pointing towards the coil 1. And then you see these wirings, how they are connected. Coil 1 is connected to coil 3, and then these are the two terminals. Terminal A right now is positive and terminal B is negative. And if we see the other two coils, coil 2 and coil 4, they are also connected, and then these terminals are the C and D. So based on the circuit, when A terminal is positive and B is negative, that is the first position. So in that position, when this is positive, when the positive current, when the current flows in this direction and then it leaves from here, then in that situation, the rotor will face the coil 1. And then second mode is when C is plus and D is negative. So when C is positive, which means this becomes positive and this becomes negative. And when the positive supply is given here, then this will be energized. Then what will happen? Then this rotor direction will change, and it will try to move towards this direction, towards the left. That will be the second position, and that's what we see here. The position at that moment is this. This is the second position. So rotor will point towards the second coil. And in the third case, when A is negative and B is positive, which means giving the negative, connecting the negative portion of the supply to A, and B is positive, then this coil will be energized. And then in that case, your pointer of the rotor, it will move towards the third coil, and so on when the fourth coil is energized. And for this to energize, this D has to be positive with respect to this C, and this will be negative. So at that time, the rotor will point towards the fourth coil. So this is called your two-phase or bipolar stepper motor. So here the term bipolar, it applies to this motor because the current is sometimes reversed, and that's why we use this term. Now let's see next. Now next is the two-phase stepper motor, which is continued, but this is the dual mode. Dual mode means two coils are energized at the same time. So as you can see, in the first case, when A is positive, B is negative, C is positive, D is negative. So this is positive, which means this coil is energized, and this B is negative. And then C is positive, this coil is energized, and then this is D is negative. So in this case, these two coils are energized. If that's the situation, then the rotor points towards this position, which is called your 1 dash. If you apply the power for each case like this, for example here A negative, B positive, C plus, and D negative, then you will able to achieve the 2 dash position, which is here. The rotor pointer will move towards here, and then so on. You can achieve 3 dash and 4 dash position if you use this circuit polarity. Now here, the second picture which you see here is the 8-step drive using a half step. So this one you already know. In this, what do you have to do? You will energize just one step, and if you do so, then the rotor will point towards that energized coil. So in this case, A is positive, B is negative. So that's why your rotor is pointing towards the A coil. So in this dual mode, having two circuits being on at the same time will produce more torque when compared with the single excitation mode. But however, in this one, more current is consumed and the controller is more complex. Still, because it produces the greatest power to weight ratio, this bipolar with a dual excitation mode is very common. Now let's see next. So next is the four-phase stepper motors, and it is the most common type of stepper motor, which has four independent field coils, and these can be energized. And then the direction of the current in these stator field poles, they are in the same direction, and that's why its name is unipolar, because the current is will be in the same direction. So in this type of stepper motor, the control circuit is very simple, because the poles can just on and they can turn on and off in sequence. It does not have to reverse the polarity of the field coil. And if you want to increase the torque for four-phase stepper motor, that can be done by energizing the two adjacent coil together, the way we saw in the previous slide. If you energize these two together, then what will happen? The rotor will align in this direction. So it will be somewhere in between these two poles, and that similar can happen when you energize these two or these two, then the rotor will set into that particular direction. Now in this, if you want to rotate the rotor in a clockwise direction, then you can just follow this sequence by energizing AB coil. Then it will be in this position, which is it is currently on. And then if you energize CD, then it will move to the, it will align towards this coil, and then so on. Now next is the four-phase stepper motor with center tap windings. So in this type of stepper motor, this can be operated in two modes, the two-phase mode and also in the four-phase mode. So when this type of center tap winding four-phase stepper motor is used in two-phase mode, at that time the center tap windings, they are not used. So if you see here in the wiring diagram, you will see if we don't look at these two wires, then it is just like a four-phase stepper motor. And with the help of these wires, a center tap has been created, which you can see here, the terminal 2, 5, these are the center tap created. So this 5 terminal is the center tap between the 6 and the 4 coil, and this center tap 2 is between the coil 1 and the 3. So here in this symbol diagram also you can see the center tap. This 2 represents the center tap and the 5 represents the center tap. So when you're working on a two-phase mode, then these the 2 and 5 center tap can be ignored, and when you're working on a four-phase mode, then the center taps become a common return, and the power is applied to the 1, 3 and 4 and 6. So this was the four-phase stepper motor with the center tap windings, and this is the end of the lecture. Thank you so much for watching.